All right, so it's just a couple more things that I want to do for the class. One is basically what is known as the structural idealization. Okay, and it's something that I believe you should have covered a little bit in structures 1. Okay, so basically what is the structural idealization? So let's say we have the real structure that, let's say we do a wing box. Let's say you can have here okay, let's say 4 plates that are like welded or riveted to each other. And this would be the idealized structure. So what do we do in the idealized structure is what we have been doing the whole semester. You replace all the structure, let's say by boom areas, no? So the question here is, how do you go from the real structure to the idealized structure? Have you done a bit of this in structures 1? Okay, so I'm going to go kind of quick on it, but just want to do a review. Okay, so all right, so for the process of the idealization, the most important parameter to consider is, or R, or okay, let's just say is the moment of inertia. Why is it the moment of inertia? Because if you remember, the expression for the stresses is generally what? Of the type my over y. This is the load. This comes from the geometry. This is also from the geometry. Sometimes you also have the shear. What is the shear? Then it will be, let's say, IT or whatever, V YT ds. Or this was equal to what? V over I B sub R Y sub R, okay? The summation sign. Sorry, this is a B sub R. But basically, you see that here the important parameters is the Y, is the I moment of inertia that comes every single time. Okay, it's in the stresses, it's in the shear flow, everything we've been doing throughout the semester. So so we're going to base our idealization in trying to keep the representation of the moment of inertia between this model and this model. Okay, so first we're going to look at the vertical members. So this one and this one over here. Okay, so let's say our vertical member. Let's put the location of the neutral axis. And we use the normal notation. Let's say the width of this panel is B. and the height is h. So this is the real structure. We want to go to our idealized structure. That would be what? Something like this. So obviously, something extremely important to keep is, let's say, will be the geometries of the height. If you have any questions, you can stop. So what would be the moment of inertia for this structure? Let's say about this axis. Let's say about the x. What would be Ix? Would be what? 1/12 of what? BHQ. Perfect. So now what do we want? Want this to be the same. So what will be the area of inertia of this one? What is the equation we have been using? The B sub r, y sub r squared, no? Yeah? So this should be equal to what then? 2 times, let's say B, they are equal. Okay, in this case, let's say equal B1 equal B2 for simplification. Times what? H over 2 square, no? Okay, so obviously here, if you want, I'm going to put it. I'm doing what? What is the assumption I did over here? Thin structures, no? That we say that the skins does not add any stiffness, no? Okay, so let's say T equal to 0. That's the assumption we have been doing all the time. Okay, so now what are you trying to do? This needs to be equal to this one over here. Okay, the real structure to the idealized structure. Okay, so let's say over here from previous page. What do we have? Ix equal to 1 over 12 BHQ needs to be equal to 2 times B H over 2 squared. Okay, so if we just look at these two terms over here now. All right, so let me do some math, basic math. 112 BHQ will be equal to what? B with 2 H squared. So you can see that you can cancel this H here with these two over here. So we're gonna have, let's see. Okay, 1 over 12 BH equals to B over 2. So we're trying to solve for B. So what should be the area B? The boom area should be BH over 6. Generally, I leave it this way, but some books do this notation. What is really BH? Is the area of the panel, no? Okay, so generally, I like to leave it that way, but some books like to present it this way. Okay, and if you started working on the project, the Nastran project, basically is the same idea. If you look at the calculations, what are you trying to model for the stresses? The moment of inertia of what would be just one panel, simple panel, no? Okay, you have the simple panel. So that one has an I, no? Whatever, 1/12 over BH cubed. Now, if you put reinforcements, what's going to happen? Those reinforcements are going to make the structure stronger, correct? And what you're trying to do actually is you're trying mathematically replace the, let's say, the thin panel that has the stiffeners by an equivalent plate, which would be just thicker, but that has the same properties. Does that kind of make sense? Okay, that's what you're supposed to do in the project. So anyway, this will be here for the vertical members. To go from the real structure to the ideal structure, the area of the boom area will be the area of that panel divided by 6. Now we're going to look at the horizontal. So we look at the vertical, let's look at the horizontal. Members. Okay, so exactly the same thing. This time, instead of having the member to be vertical, we're going to have it horizontal. So again, imagine the real structure. So now our neutral axis will be here. All right, so you have this structure over here. All right, so if you want, let me do this. So we first idealized the vertical member. Now we're doing the horizontal, no, but it's about the neutral axis. So that's the first one we did here, the vertical. Now we're doing the horizontal. So for thin members, we can assume this will be the distance to the neutral axis will be h/2. The length of the panel, let's say, is L. And that the thickness of the panel, again, we're going to call it B. And what we want to do is what? Want to idealize that with two boom areas. Okay, so let's say here B1, B2. Again, this will be H divided by 2. Okay, so that one's a little bit more complicated. So let's see. Here will be the real structure. This is the idealized structure. So what will be the Ix for this member over here? What will be the moment of inertia? What is the moment of inertia of this member over here? 1/12 of what? LB cube, correct? But this is about this line over here, no? Now what do you need to do? You need to move the moment of inertia that is here. Where do you need to move it? To the neutral axis. What do you use in order to move it to the neutral axis? You use the parallax theorem. So the parallax theorem will be what? Plus A, that will be what? I mean, let me put A if you want initially. A d squared, that would be H divided by 2. Okay, so now thin structures. Thin structure assumption is what? Is assume that B is much, much lower than the length, no? So then what can we do? We can neglect that term. All right? Okay, and now here, what would be the moment of inertia? We need to do the same thing. What would you have? So what would be the moment of inertia of this one? Will be 0 because there's nothing. So how would you find this one? Would be what? Would be what? B1, 1 squared plus B2, y2 squared. So this will give you what? 2B. And what is y? H over 2 squared. All right, so if I do the two expressions, what do I get? A over H over 2 squared will be equal to what? 2B H over 2 squared. So if I do the mathematics here, we find that the equivalent boom area that will represent this should be equal to what? A divided by 2, or what would be B times L divided by 2. I mean, I think this should not be 100% new, no? It's a bit of a review, no? Okay, so that's why I'm going a bit fast. So 3 example. Okay, so imagine that you have here a wind box. So as before, this is made out of the 4 panels that we had before. But in addition to that, we're going to have here some corner stiffeners. Let's say area B1, A1, A2, A4. And you know that A1 equals to A2 equal to 0.5 sorry, in square, and A3 equal to A4 equal to 0.75 in square. Oh, and let me give some more geometry here. So now it's a wind box. Now you give some aerodynamic shape. So let's see, that distance here will be 48 inches. The depth will be 8 inches. 1, 2, 3, 4. And let's say the panel of each one, the thickness of each panel will be pretty thin, 0.05 inches. So we can use the thin panel assumption. So for this problem, we need to determine idealization of the structure. Let's say to determine the direct stresses for mx equal to 500,000 pound each, and my equal to 100,000 pound inch. So what does that mean? That the coordinate system is going to be x Okay, so part A, let's do the idealization. So basically what we want to do is to find our idealized structure that would be, what would be here? B1, B2, B3, B4. All right, let's put some values. So we have here, this will be L, this will be H, and one will be a thickness T, but that will probably be ignored. Okay, so let's see. So B1, so B should be equal to what? So area of, I'm looking at this term over here. So let's say those stiffeners over here, okay? So let's call this one, let's call them stiffeners. Sorry. These ones over here, these areas over here, let's say these are the stiffeners, not on the corners, correct? So let's say the B's should take into consideration the area of the stiffeners. Plus what? Area of, which one do we do first? The vertical members? Area vertical or vertical member plus the area of the horizontal member. So basically it should be equal to what? Should be equal to the A. So this one for the area of the vertical members. Okay. So this should be what? This should be the area, let's say areas A. Plus what was the equation we had for the vertical members? Okay, plus area. So let's say this is stiffeners plus A vertical over 6 plus A horizontal over Okay, so I'm just going to go to the next page and rewrite the same equation. Say from previous page. E would be equal to the A stiffeners plus A vertical over 6 plus A horizontal over 2. Okay, so what would be B1? Oh, we cannot see. What should be B1? What is the area of the first one? I mean, let's put the, should be what? A stiffener 1, no? We do this way. We should be this one over here. So A1, if you want, we could do to the next line. So it should be equal to what? 0.5. Yes? Okay. Now, what should be the area of the vertical ones? What is the expression we find for the vertical? What should be the area of the vertical? Okay, so let's do symbolically. So HT divided by 6, no? And now, which is H is how much? 8 times 0.05 divided by 6. I don't have the values, but basically we have this one. And what should be the last one? What would be the horizontal? L times T divided by 2, so plus 48 times 0.05 divided by 2. And if you do this calculation, this is going to give you that B1 I found here to be equal to 1.7, but you can do a calculation, 1.767 inch squared. Okay, so similarly, we do the other one. So what should be the other one? Should be just what? A2 plus, should be the same thing, no? HT divided by 6. So we're doing this one now. This one over here, okay? It's basically the same as this one, no? The only thing that's going to change is the area. Plus L T divided by 2. I think to save some time, just basic numerical application. We'll find that B2 should be equal the same thing as before. Since A1 equal A2, we're going to get the same value, no? Now we move to A3 and A4. So E3 will be equal to what? A3 plus more of the same, HT divided by 6 plus LT divided by 2, which is going to give a value of B3 of 2.017 inch squared. And finally, B4 would be equal to A4 plus, again, more of the same, HT divided by 6 plus LT divided by 2, which will give you a value of B4, the same thing as the other one, 2.017 inch squared. Okay, so what does that mean? That now we find the idealized structure over here. Over here. B1, B2, B3, B4. Okay, if you want, you can do this stuff that is just over there for the shape. We don't take them really into consideration in this case. But basically what happened over here, is this cross-section symmetrical or non-symmetrical? B1 equal B2, but B3 equal B4. Is symmetrical or not? So it's non-symmetrical, no? So let's say which one is heavier, B3, B4. So if you look at the location of the neutral axis, it should be what? It should be a little bit lower than the middle, no? Since it's heavier at the bottom. So let's say the neutral axis, I make it up randomly, I make it up over there. Okay, so if this is non-symmetric, what do we need to do? We first need to find the position of the CG, no? Okay, so, all right, so let's do that. So which one do we do first? So Y, the location of YCG, since we did the assignment, should be equal to what? Summation of what? The B sub R, Y sub R divided by the all the areas, no? So from which point you want to start? What do you want to be our reference number? 1, 2, 3, 4? 1? Okay. So then you will have what? B1 times, so B1 is B1. Do I need to put the values? You can just put Y1. What will you have over here? So this will be what? If I start at 1, what would be the Y? 0 plus B2 what? 0, no? Plus B3 times what? 8 plus B4 times 8. Maybe I need to put negative 8. I was just thinking about negative 8. Sorry for that. And all this stuff should be divided by what? B1 plus B2 plus B3 plus B4. If you do this calculation, you find that Y bar will be located at minus 4.26 inches. Okay, now since B1 equal B2, B3 equal B4, you're gonna have an axis of symmetry over here, no? Actually, it's symmetry. Sorry for that. So this is symmetrical cross section. It is symmetric. Symmetric about one of the axes. No, since B1 equal B2 is symmetric about this axis, no? Okay, so basically we know that the CG location will be where? Will be somewhere over here. So this distance will be, I'm going to do this. Might be too much on this figure. Yeah, I'm gonna go to the next figure, but I'll redo this figure. So what will be that distance is 4.26. And now in the middle, what will be the location of the CG? From here to here should be what? Since it is symmetric, should be equal to what? 24, no? Okay, so maybe we have space over here to do this one. So IXX should be equal to what? The summation B sub R Y R squared. I mean, you just did that one, the assignment. So what should be this one? B1 times what? What will be the first one? What will be the distance y bar 1? 4.26 squared plus B2 times what? 4.26 squared plus now B3 times what? Whatever that distance is over here. What should be that distance over here? Yeah, I think I have it somewhere here. Let me look at it. But yeah, 3.74. So it's too much on the same figure. Can you guys see at the back, or do you want me to zoom? You need me to zoom? It's good? Okay. So this should be 3.74 square. So actually it should be negative, no? 0.374. It's not going to change because it's square, but before minus 3.74 square. And if you do this, you get that IXX, it will be equal to 120.8 inch to the 4. Okay, so now we're going to do the IYY. So the IYY should be equal to what? The summation of the B sub R times so what do we have? X and Y. So X, no? Do we use X and Y? So it should be the X sub R square. So what do we have? B1 times I think it's 24, no? For what you just said. What is that page? I lost it. Okay, yeah, here it is. So will be here is either minus 24 or 24, no? Okay. So B1 will be negative 24 square plus B2 times positive 24 square plus B3, that would be positive 24 square plus B4, that would be negative 24 square. And if you do the calculation, this will give you that I, y will be equal to 4,359 inch to the fourth.
Why don't we use parallel axis theorem?
Yes, we need to use it. Sorry, I was just going straight forward. So basically, the I mean, that's what we did. Yeah, because okay, I think I understand. Yeah. Yes, because what happened is this: is that in both cases, what is the simplification? If you look at the IXX, no, about this axis, what do? We are assuming that the I of each one of these members here is actually 0, no, because we assume it's thin. And then what we're doing is moving this one to here, no, which is what this term is doing. This is the second term of the parallax theorem. Does that answer your question? No.
Yeah.
And we're doing the same thing over here, but for these members, no? Okay. Okay, so we did this. So structural idealization. I mean, we should have put that maybe in 1 or 2. Okay, doesn't matter. So let's say part B. I'll put A and B. We're going to calculate the direct stresses. U2 MX equal to 500,000 at the inch, and My equal to 100,000 at the inch. Okay, so let me do a figure over here. It's always important to do figures because figure is what show me that you understand the material. I need to see figures related to an equation, and that is what shows me that you understand the. So let's say this will be 1, 2, 3, 4. Our neutral axis. Okay, so if this is the XY, in what direction would be the normal stress? There are 3 options: X, Y, or Z. Remember what I just said, normal stress. What will be the direction? X, Y, or Z? It will be the Z. Do you understand why? Because basically we have our cross section. Let's say this is XY. That will be expanded, no? Yes? Normal stresses will be on this span-wise direction, no? Yes? Yeah? All right. If you want to look at this, this should be Y, so X, Y, and Z. Z is the normal direction. Okay, so Z, now, Let's just do one. Remember, I like to look at the sign by the understanding. So we have mx and my. So this is bending about mx. So mx will be what? So generally the notation is what? Counterclockwise. Will be the moment, no? See, I don't memorize the equation. It's just understanding. So if this is the moment, this will be bending about what axis due to this moment? Will be bending about the ixx or about the iyy? Will be bending about this axis, no? Due to this moment. So what is going to resist the bending? Ixx. And now we can find these stresses at what locations? 1, 2, 3, and 4. So what is the distance from the neutral axis to 1, 2, 3, or 4? In what direction is it? Why? You see, you don't need to memorize the equations. With understanding, you get them back. So now, if the moment in this problem, they tell us that it's positive, 500,000 newtons. So that will mean that 1 and 2 should be what? Tension or compression? Let's see, can we agree? What are we going to have? Tension or compression? Okay, so this will be bending. So mx 500,000. So let's see what I have here. I mean, depends which point. Which point are we talking about? This one, no? Yeah, so that one should be then in tension, no? Okay. So yeah, the thing is that we need to specify which point. So let's say make all those calculations. Let's say at point 1. Okay.
I was just curious. So we're doing the moment MX first, and then you go and Y,
Yes.
and then we combine them.
Correct. Yeah. And the reason we can do that is because we assume that every deformation is linear. So you can use the principle of superposition if you want to think about mathematics.
That's why we don't have forward thinking.
Correct. But even if you have the whole equation, that's what, even if you have all the terms, you can just put the ix up, but just assume the other one to be equal to 0. Okay, that should not affect the sign. Okay, so this one we know would be in tension. So do we need to change something? That's why I like to use the absolute value. So this is positive, and this is positive. This value will be positive, no? So we can leave it as it is, correct? All right. Now, let's look at the moment. Now we look at the moment, my. So what should be the equation? I don't put any sign. It would be my. And when you created my counterclockwise positive, that one would be now bending about which axis? You're bending about this one over here, no? Yeah. So that one will be what? Iyy. And this time about this axis, the location of points 1, 2, 3, 1, 2, 3, 4 will be in what direction? X. So tension, positive. Okay, that's what we know. So now let's do the same reasoning over here. If we do the moment my in this direction, will be in tension or compression? One will be in tension or compression? Will be in tension as well, no? Yeah. Tension, positive. But maybe now we might have to be careful because here x1 will it be positive or negative? We need to be careful here, so because so this side will be in tension, this side will be in compression, no? So what do we need to do in order to make the equation work? I have to add a minus, no? Because this x will also be negative. Or you can just, I mean, personally, I would not put this, I would just use the magnitude. But if you want to be accurate, you can do whatever you want. If you want, we can put plus, but because really x1 will be equal to what? negative 24, no? Yes? And x4 will be negative 24. This will be positive 24, and this will be positive 23, 24, no? Okay. Okay, so I don't have values over here, so maybe let's just do the stress test at 0.1. So this is going to give us what? 500,000 times y. What should be the y? What was this value? 4 point something, no? 4.36, 4.26. So 4.26 divided by here's my page 4 over here. Divided by 120.8 minus my is 100,000 times x will be what? Negative 24 divided by, I have it right there, 4,359. So can someone please do that equation here?
Thousand.
18,000. Okay. I mean, I'm going to introduce something here, but then we'll do it in more detail, okay? And then can we maybe do here at 0.2? And we'll stop over here. So let's see, at 0.2, what will you have? Due to the mx, what did we say? We said the top was going to be in tension, no? So it will be still the same thing, mx times y divided by the ixx. But now 2, will it be in tension or compression? It will be in compression, no? So basically we can use the same equation here. So minus my times x divided by iyy. But this time, if you do the calculation, what do you get for sigma z2? So the only difference is that here this x is going to be positive 24, no? Instead of negative 24. Yes? It's the only difference. So what will you get for the stress over here? $17,081. So I will do a problem with you later on, okay? And we'll do that in more details. But to tell you the truth, in real life, for example, if you needed to calculate the shear flow due to this, and it's basically what we did because it's straight, no? It's basically the same assumption. What could be a good approximation of the shear? Look at this. Shear should look at the difference, do the difference of these two stresses, and divide that value by the distance here, which is 48. How much? Okay, so if you want an approximation of Q12, I'll do a problem in detail because this is the way it's really done in real life, to tell the truth, without using the completed equation. You can say that Q12 is approximately equal to sigma, let's say Z1 minus sigma Z2 divided by the length between those two, no? Okay, and what do you get? You said 22 point something? 22.9. Oh, sorry, I didn't. What did I do here? You need to multiply by L. Otherwise, we'll have, yeah, multiply by L instead of divide. Sorry. So we have LB per inch. Then you have a large value. What do you have? 52,000. Okay. Yeah, it's something, yeah. Yeah, but initially, what happened is that when I was thinking about Q, we do problem detail. So what I was thinking is that Q is equal to the difference of the axial force PC, PC1 instead of the stress. I mean, let's redo this, okay? Let's redo this the normal way, okay? This, let's see. All right. Instead of going fast, I will do here. So let's say shear flow approximation. So let's do more or less the same thing that we did. So our shear flow approximation should be equal to what? PZ1 should be equal to what? Sigma Z1 times B1, no? Same as the assignment. And PZ2 should be equal to what? Sigma Z2 times B2. So can you please do the sigma Z1? So 18,183 times, what is B1? B1, we found B1 to be equal to 1.767. So what do you get? Here's B1. And if you do the stress, what do you get? So 18,183 times 1.767. 129. Okay. And now if you do the 17,081 times the same thing, 1.767. 30,182. Okay. Okay, so what I'm saying is that a good approximation for the shear flow of Q12, okay? We could use the complicated equation as we are doing on the assignments, but in the real life, what you can do is PZ2, let's say, or PZ2 minus PZ1 divided by the length of L12. That's what I was trying to do, but it didn't work for the stresses. So you will do, let's say, 30,182 minus 32,129 divided by 48. I think it's 48, no? So what would that give you? By 6 LB per inch. Okay. So yeah, negative. We just mean that it's going on the opposite direction.
So what was the assumed direction?
Yeah, 1 to 2. Okay. And to tell the truth, I mean, you see here that instead of using the complicated equation of the V divided by I, so on and so on, This is basically the only thing that I'm doing, no? And okay, so the idea from now on, I'm just gonna want to cover one quick thing that we'll do it next time, but let me show it to you. It's something I want to mention. I think I actually just downloaded this stuff here. What is it? Yeah, buckling of plates. It was here. It's from, it doesn't matter, it's from MIT, I think, but don't worry about it. That is MIT. But basically, we talk about the buckling of plates, no? So basically, what do we say is that we say that when you have a structure of an aircraft, all the different panels are riveted, no? Okay. So let's say if the wing has lift, so that means that it's going to be like a smiling face, no? So the top of the wing will be in compression and the lower will be in tension. But what happens when you put a panel into compression? Once you, at the beginning, nothing's going to happen, but as soon as you're going to reach a certain value, by pushing in, it's going to buckle, no? Okay. So buckling is a complicated problem because it's not really a, if you want, a structural problem from the point of view that it's not like the structure is slowly deforming. It's not proportional to the force, no? When you keep the notepad this way, I keep pushing up, you put force, but it's not deforming. All right. So it's not deforming, but as soon as you reach a certain force, then it buckles. All right. So the buckle is not proportional to the force. Basically, the buckling is more related to vibration, is a stability problem. It's either the panel is stable, but as soon as you reach a certain force, the motion, or if you want, the stability of the panel becomes unstable, and what happens? It buckles. Yes, does that make sense? Okay. So when you solve that with analytically of finite element, basically it's a complicated equation. Okay. you look at the deformation and all this stuff. If you take a graduate class called method of plates, this is the plate equation. Okay. But basically, and this would be the nonlinear force, the nonlinear in-plane force that you put, blah, blah, blah. You will end up with some expression. You end up to this expression, which is the value of the actual force you need to produce. Oh. Sorry for that, guys. I thought you were looking at this stuff. Sorry for that. So basically, let's go back to the beginning. So basically, I will add this document online. Basically, what is buckling? This is like what I was doing with the pad. This might be a panel. Now you apply an axial force. Okay. So this panel is either going to be stable or unstable, no? Okay, until it buckles. So it's a complicated problem because you have a nonlinear in-plane force. Okay, so this is two-dimensional. This is from a class which is called Theory of Plates and Shells. It's a graduate class over here, at least. And basically, you see here, buckling of simply supported. So the buckling is going to depend on the boundary condition of the panel. So for simply supported and clamp supported, you can find a solution. Basically, for simply supported is the simplest case. And if you solve that equation for that load here, the actual load, you find that it's equal to K C pi squared over B squared times D. Okay. And generally, you find these values from a table. The value for the K over here. So we do one example later, okay? But just to show you that this is not an easy problem, but that you need to be aware that when you do the design, you need to make sure that your panel is not going to buckle. So basically that the load N over here, when you do the design, the load N over here is under your design loads, no? Because you don't want your panel to buckle. Does that make sense or no? So generally, you will have to increase the thickness. That's the easiest way to increase the thickness. But again, I will talk a little bit more about this next time. I have a question for you guys. Because